Because now it's not asking me.
It says webinar is now live stream on YouTube. Let us check.
Setting up you. Please just try. Just hold a few seconds. Setting up your webinar for YouTube Live. I'm getting the message. Done. Redirecting to YouTube. Just see whether it is live.
Yeah, yes.
It says webinar is now live stream on YouTube.
Just see.
Let
now
us check.
Please just try. Just hold a few seconds. Setting up you. I think now let's see whether it is live. I'm getting the message. Done. Redirecting to YouTube. Now it should be live, I hope. Just see whether it is live.
Yeah, yes.
It says webinar is now live stream on YouTube.
Not yet. Just see.
Let
Now
us check.
I'm getting the message it is live. Seconds. Setting up. I think now let's see whether it is live. I'm getting the message.
YouTube level.
I'm redirecting to YouTube. Just see whether it is live.
Yeah, yes.
It says webinar is now live stream on YouTube.
Not yet. Just see.
Let us check.
I'm getting the message it is live.
Yeah, now it is streaming, I think.
I think it should be streaming now. Let's check. Yeah, it is streaming. It is live. It is live. It is live.
Now it is same.
I'm getting the message.
Yeah, now it is streaming, I think. Yeah, now it is.
Sir, it is live now.
It should be. It is streaming. It is live. Let's check. Yeah, it is streaming. It is live.
Let us start the proceedings.
Let us start. Let us start.
Yeah, already we have lost 20 minutes. People
Yeah, now it is streaming, I think. Yeah, now it is.
Sir, it is live now.
Somebody is playing this YouTube live in the background. Noise
Is it
is
okay
coming.
now?
Please.
Is it okay now?
Yes, yes, yes.
Yeah. So let us start.
Start. Okay. Good afternoon, all. I welcome all to the weekly online lecture series on radar meteorology, organized by Southeastern Meteorological Association and Advanced Center for Atmospheric Radar Research, City University of Science and Technology. Today we have the lecture number 19. Okay, the speaker is Dr. Abhilash, Director of ACARR CUSAT. This taking the lecture on the topic application of Doppler radar in research. So before start of this lecture, I will invite Professor Someshwar Sir, President of SAMA, to the welcome address.
Okay, thank you very much, Mr. Rakesh. Good afternoon, everyone. Professor ABM Tyagi Saab, the President of SAMA. Today's distinguished speaker, Dr. S. Abhilash. He is also our host, as you know. He's the Director of the Advanced Center for Atmospheric Radar Research at Cochin University of Science and Technology. Well, he is a well-known researcher. He is not only the director of the ACARR, but also has been working both on the application of radar on the modeling, as well as assimilation of radar data in the models. So he's got a lot of experience. So today's topic or today's talk is going to be very, very interesting because many of you, I know, may be interested in utilizing the radar data for different purposes, not just the research on the core radar or the technical aspects of radar, but also most of you will be interested in the application of radar data in the models and many other things. So Dr. Abhilash is the most, the best person for that talk on this subject. Since he is also the host, so I don't have to tell you about the background of this lecture series. Already, you know it has been shared many times. And therefore, without delaying much, I'm sorry that we are today late by about 20 minutes, 25 minutes because of some technical hitch. But without any more delay, I'd like to wish you to have a nice session and go ahead. So, Dr. Rakesh, on to you.
Thank you, sir. Now I invite again retired Professor Tyagi Sir for the presentation address.
Thank you, Rakesh, and I join Somesh for extending the welcome to all the participants, and also thank Abhilash for agreeing to deliver this lecture, apart from being the host of this 20 lecture series on the radar meteorology. Well, he is the right person, being the director of the center which promotes the atmospheric radar research application. And as Dr. Somesh has mentioned, that his experience both in the application part as well as the research part is going to be a great asset for all of us. And I'm sure this lecture will benefit all of you, because the radar data is so precious, and its availability is now becoming much easier as compared to earlier days, and the number of radars also increasing. So I'm very happy that its utilization both for operational part and also for research is being covered in our training program. And today's lecture is focused on the application of Doppler radar on the research. So make best use of it. All the best.
Thank you, sir. Now I invite Dr. Rohini Alba madam to give a brief introduction about today's speaker, Dr. Abhilash.
Thank you, Dr. Rakesh. So, yeah. So, quick brief introduction of Dr. Abhilash is he completed his MSc in Meteorology from CUSAT with first rank and distinction, and doctoral degree in Atmospheric Sciences from CUSAT in the year 2009. He also started his scientific career as senior research scientist, Blackstone Insurance Bermuda Private Limited. Worked at Indian Institute of Tropical Meteorology at Scientist C and as Scientist D also from 2009 to 2016. He also worked as visiting scientist, University of Miami, from 2014 to 15, and National Center for Atmospheric Research in 2014. He joined Cochin University of Science and Technology as assistant professor in 2016, and presently he is holding the position of director, Advanced Center for Atmospheric Radar Research, CUSAT. He was bestowed with SARC Scientist Medal for the research work on the assimilation of IMD Doppler radar wind observations in a mesoscale model for the short-range prediction of convective storms during 2007. He also received Indian Meteorological Society, that is IMS Award on Weather and Climate Services in 2017. He also received Best Young Faculty Research Award of CUSAT in the year 2019. He received the T. Peter Memorial Award in recognition of the meteorological and climate services he provided to artisanal fishermen. Dr. Abhilash made an outstanding contribution in the design, development, and implementation of operational forecasting systems in the short, medium, and extended range to predict high-impact weather events over the Indian region. His innovative work includes customization of forecast products for impact-based forecasts, dissemination to various stakeholders, including fisheries and farmers. He has more than 19 peer-reviewed publications in international journals and co-authored more than 16 books and book chapters. Written more than 60 popular articles on weather and climate for prominent periodicals and newspapers. Increasing public awareness of climate science through various print and visual media is his forte. He has delivered more than 210 popular lectures related to weather and climate sciences. He has chaired sessions in many national and international conferences and organized many national and international seminars and symposium. He is handling many research projects from leading funding agency with total outlay of more than 21 crore. So I invite Dr. Abhilash to please share his screen and go ahead.
Thank you, madam. Now I invite Dr. Abhilash to the lecture.
Thank you very much, Sama, for selecting Advanced Center for Atmospheric Radar Research in hosting this
event, the radar meteorology course, and also giving an opportunity to talk about the applications of Doppler weather radar in research. So before going to the talk, I wish to dedicate this talk to my guru, Dr. Somesh sir. Because of him, I am sitting here, because I started my NWP career with him when he was at NCMRWF. We started, that is the beginning of my NWP career. So I owe all my success to him. And so if you look at the enemies, yeah. If you look at the radar applications, mostly the radars which is used in meteorology, which is the functionality is dependent on the wavelength. If you look at the frequency and corresponding wavelength, most of the application is depending on the wavelength. If you look at the radar equations, like the back scattering cross section, it has a strong functionality or the dependency on the wavelength. Like, for example, if you look at the scattering cross section or the Rayleigh May region or optical or the geometric scattering, and all depends on the wavelength. So, and if you look at the radar equation for the point target on the left side, and which is also a function of radar wavelength, operating wavelength, where the received power is a function of radar constant. The first term is radar constant, and second term is the radar parameters. And the third term is related to the target, both the scattering cross section and also the range of the target. And if it is a distributed target like DWR or the clear air radar, that also, if you look at the power received, the equation, radar equation for the received power, we can say that it is a strong function of radar wavelength and also radar reflectivity factor is a. So that means, and if in the case of clear air radar, the bright scattering or the turbulent scattering, which is even then also is a function of radar wavelength, and the PN square, which has a strong dependence on the radar wavelength. That is why, if you look at the different applications in the across different wavelengths, we can say that depending on the factors, these are the some of the factors influencing the selection of the wavelength. This is with respect to our radar. 1.46 meter is the 205 megahertz wavelength. So that central line is our wavelength. So the selection of the wavelength is determined by many factors like atmospheric existing atmosphere and also the antenna structure, arrays, cosmic noise, and many other factors. And if you look at the vertical, in the case of clear air radar on the right side, the vertical coverage of this radar is determined. Basically, it is also with respect to our radar 205 megahertz. That is the central vertical line. Based on that, if it is based on the observed altitude range is a function of the frequency and also power aperture product. Our power aperture product is something around 10 raised to 8 watts per meter square. So it is going up to a level of 24 kilometers. That is depending on the background noise and the power aperture product, and that is what it is going up to 24 kilometers. So that means most of the weather radars in the atmospheric application or any other application, which has got determined mostly based on the radar wavelength. So this is the table taken from Wikipedia. And also, if you want to look at more on this, because my talk, because most of the things many speakers have already covered, in which Dr. Pradhan sir has covered different type of radar wavelength and the application of that specific wavelength. So all are request to refer all these previous lectures like Pradhan sir's lectures, Thambi sir's lectures, and T.N. Rao sir's lecture, Suresh sir's lectures. They are, and I'm referring some of the slides from them, and then and if you look at the selection of the meteorological radar, like the weather radar, that is mainly based on the trade-off between the measuring range of reflectivity, the range, and also the attenuation, signal attenuation based on the wavelength, and also the cost of the radar and the terrain features. These are the some of the factors which leads to the selection of particular wavelength based on not only based on the application, if the cost is another determining factor. And if you look at the mostly the weather radars are classified into three bands like S band, C band, and X band. And where the S band has, each one has its own merits and demerits, all because combining all together will make a very good observation of the atmosphere. If you look at the S band radar, it is very good at a longer range, like up to maybe 250 to 300 kilometers, and is least affected with the attenuation. So, and another thing is that the quantitative precipitation estimation can be valid up to 200 kilometers, and there are certain glitches, means drawbacks like beam broadening, beam width, and all. But that is the limitations of S-band radar. And another thing is that the data corrections are more robust and easiest to implement in the case of S-band weather radar. However, these are the very expensive radar because considering the large aperture and the antenna array systems and all, and even the electronics. And this, coming to the C-band radar, they are a compromise between high frequency radar and the low frequency S-band. Between X and S band is a compromise, and it gives a reliability, means good reliability for short distances, maybe up to 150 to 200 kilometers, which is less expensive than S band radar. And also attenuation is slightly higher compared to the S band radar, and thus quantitative precipitation estimation is more accurate up to a limited range of like within 100 kilometers. And then comes the X-band radar. They are mostly called as cloud radar because that is, as the name implies, that is a frequency which we are mostly used for deriving the vertical, more microphysical structure of the clouds. So that is why it is a but the range is very limited. It can probe up to a range of like 50 kilometers, less than 50 kilometers. So that is what one disadvantage, but still the attenuation is also another problem because that also limits this QP, quantitative precipitation estimation, to be limited within 30 to 40 kilometers. And also this is very least expensive radar because considering all radar electronics and other hardware, it's a very least expensive radar in the category of the S-band radar. So these are some of the radar which is being widely used for weather applications. And if you look at the products, basically the technical details and the level 1 products, how the reflectivity is being derived, all this is being covered by the eminent speakers before. So what I mainly focus on is the level 2 and level 3 products, because level 2 products in the case of single polarized radar, they are nothing but the kind of Doppler reflectivity and the velocity, and also the spectrum width. So these are the basic 3 parameters or the variables which is pertaining to the single polarized radar. In the case of dual polarized radar, we know that ZDR, correlation coefficient, or the differential phase, and also the KDP. They are the most useful parameters when it comes to dual polarized radar. They are the base data. They are considered as the base data. And based on that base data, we derive level 3 data, which is pertaining to, there are 2 classes in that, the reflectivity products and the velocity products. The reflectivity products are the storm identification tracking products, hail index, precipitation classification, and the composite reflectivity, radar echo type, like bright band structures and all. That is related to the reflectivity derived from the level 2 products. And then the velocity products are mostly watt products, like velocity azimuth display products from the for the velocity, and then the circulation, mesocyclone detection, tornado vortex detection. These are some of the velocity derived products. And then when it comes to polarimetric radar data, the main derived products are like the related to the hydrometeor structure, like the melting layer detection, hydrometeor classification, because the dual polarimetric radar gives the shape and structure of the clouds, and also the type of the hydrometeors and the shape of the hydrometeors orientation, and also the quantitative precipitation estimation is slightly more accurate than the single polarized radar because of the usage of ZDR and KDP. So that is what these are some of the uh, different type of radar products which is being widely used by meteorologists. So, based on the radar reflectivity, we can classify the rain according to the reflectivity. This is a very linear classification. I am not discussing much because already many speakers have covered. Not only this radar rainfall-based classification, the hydrometeor classification is also similar to this, but it depends on the reflectivity structure, more on the rainfall structure. So, the vertical reflectivity structure is the main parameter which is used for classifying the hydrometeors. So these are some of the fundamental things. Then the cyclone studies, the radars are widely used, and the structure and evolution of precipitation bands. This is also covered. So many speakers have covered this structure and evolution of the precipitation systems, and then the cloud classification, as I already discussed, basically based on the radar reflectivity factor, and also in the case of dual polarized radar, the KDP and the ZDR is also being used. And then the hydrometeor classification is being combinedly used by these techniques. And there are many type of classification schemes are there. And then coming to the wind products like sea breeze, land breeze, breeze friends can be derived, and also micro-based, and then hail detection, and the squall line structure can be estimated, and also even the non-precipitating studies like the birds migration, locust movement, everything can be detected with this type of, and also even aircraft can be detected. And these are some of the non-precipitating studies, and the heavy rainfall studies, which is also the case of Chennai heavy rainfall events. And then these are some of the known, because already many speakers have discussed much about all these applications. Now coming to the radar data, because radar data nowadays mostly used for nowcasting and improving the initial condition for the short range weather prediction. So why the significance of this radar data on mesoscale application is because the reflectivity and radial velocity provided by this radar, this contain wealth of information to be assimilated to the model. If you look at the skill of NWP skill, it is very less compared to the pure radar-based nowcasting skill. After few hours, the NWP beats the nowcasting skill. But when we use this radar data for initializing the model or improving our initial condition, that can be used to extend our useful prediction in the nowcast and short range forecasting cases. And that is why, and another problem also can be solved with radar data is initial spin-up problem with initial perturbation of this convective storms. That also can be properly represented in the initial fields when this radar data is being assimilated. And we have made the first attempts in the assimilation of Indian Doppler weather radar, the primitive version of in MM5, that is prior to WRF, the MM5 was using. So we started this work in 2005 by assimilating the Chennai and Kolkata radar, thanks to Somesh sir, Pradhan sir, and our whole team, Thambi sir, all involved in this work. So we made an attempt because there was that time the WRF was not that common. We started with UWT derived wind products as if it is coming from the radio sonde. The vertical profiles are assumed to be coming from the error structure. Everything is assumed to be equivalent to a radio sonde derived wind. So that based on that, we have assimilated, we have published a series, or maybe the probably first paper on radar data assimilation in 2007. And then after WRF came with a lot of new features like direct assimilation of radar reflectivity and the radial velocity. So that also we have done in that time, maybe around 2018-19, but the paper is got published in 2012. So this is what the history of radar data assimilation in India. And we started with the 3D war assimilation scheme, where I'm not discussing much about the assimilation part, but this is based on the optimization of cost function. So that is one part is related to the background, another part is related to the observation, where the direct assimilation of Doppler radial velocity kind of required kind of observation operator. So it is nothing but that y minus hx. So where that hx is the observation equivalent to the means model equivalent of the observation. So that we need a observation operator to map the radar observation, the model variables to the radar variables, where we compare and take the difference, and then we optimize the problem. So the observation operator for radial velocity is like this, and the observation operator for Doppler radar reflectivity, that is a mostly is a function of the mixing ratio of the rainwater content. So that is why we had to implement this observation operator in this forward models or the adjoint models. So that is why it was delayed slightly. So nowadays the WRF came up with different options, and this is what the first observation where this is the UW to compare with the UWT wind and the first gust wind. They are more almost similar. So that is why there are not much rejection when considering the first gust and the observational data. That is also very relevant, because the data has to be optimally utilized in the first guess. Based on that, we are arriving the optimum the estimation of the analysis. So that is what we started with the UW. Then we have done the assimilation in the WRF. We did actually 3 experiments, like control experiments, where without any assimilation, and then the all assimilation using the data set, whatever data set is coming through GTS, not including DWR. Then we have conducted one more experiment by including the DWR along with the node DWR experiment. So this is the results. If you look at the snapshot, we cannot find out much difference, but if you look at the difference, then we can see that the difference between the DWR and non-DWR experiments, there are a lot of difference in estimating the wind field and the temperature field and the humidity field. So when we assimilate the radar data in the assimilation system. And if you look at the difference between the even the sensitivity of the reflectivity alone assimilation and the radial velocity alone assimilation, that also if you look at compared if we assimilate the radial velocity alone, they will not produce much improvement over the much innovation vectors in the temperature or thermodynamical fields, including the potential temperature or the specific humidity. But when reflectivity alone is assimilated, that will cause a lot of changes in the thermodynamic structure. So that is why both is both is very much required when it is coming to the short range prediction. So to represent the initial fields of initial dynamical and thermodynamical fields when it comes to radar data assimilation. That is why the short range prediction is improving by the impact of this type of assimilation. Then we compared the observation minus analysis background and observation minus analysis all the way, including the reflectivity error also is minimum in the observation minus analysis. That is and if you look at the distribution, the main issue with the Doppler radar data assimilation is that the data itself is coming in the polar coordinates. So we have to convert that when it coming to the model, we have to convert that into Cartesian coordinates with the height as the vertical coordinate. So where we have to map all this polar coordinate data back to the Cartesian coordinate. That is also a very tedious job, because now many programs are available. Earlier we have done all this thing in Fortran, where we have to write all this code for converting from the polar coordinate to the native Cartesian coordinates. This is the observation. This is actually, if you assimilate the radar data, all the observation will not be taken by the radar the model. So it will reject some of the data. So these are the observation available during that time on the left side, and the observation minus background error in terms of in the case of reflectivity is like this, but in the case of observation minus analysis, that error is much reduced. So this is how some way of finding out how the radar data assimilation is improving the assimilated profiles of reflectivity at the radar location itself. And this is the case of rain estimation during a cyclonic storm, very small cyclone, Ogni. So this is the TRM. That time TRM was available. So this is a range structure of that small storm. But this is the control experiment, which is not capturing much about the rainfall variability. But non-DWR experiment, when it is assimilating with the more new data, it is capturing the variability or the distribution of the rainfall structure. But when we assimilate further the radar data, the initial condition is further improved, and we are getting more close observations, like close predictions as that of the observations. So this is what some of the impact of the radar data simulation which we can realize in the short range prediction. And this is the equitable third score for different thresholds, and that also immediately means like 12 hour, 18 hour, the impact of radar data simulation is well realized, but after that there is not much impact. But that also we need to address maybe in the future, if we come up with a very dense network of radar data that can all together if we can assimilate, that can produce. And there are different ways of assimilation nowadays, like the rain rate and the physical assimilation schemes, like estimated rain rate, or the rain structure, or the derived latent heating structure also can be directly assimilated to the model, so that the model vertical structure of the hydrometeors and the vertical structure of the latent heating can be improved. So that intent, that is the main thing, because temperature tendency, if you look at the model equation, the temperature tendency is the main thing which is very important, and that is the main, that if we can capture that temperature tendency, that tendency, the forcing term in the temperature tendency, that is mainly from the condensation or the radiation or the cloud heating. So that means radiation heating is not that much, because compared to the cloud heating, it is almost like 1 or 2 orders of higher if it is a clouds are formed, if clouds are latent heat is liberated from the cloud. If we capture that vertical profile of latent heating structure associated with the convection, different convective storms, like deep convection or shallow convection or stratiform convection, if you capture that, it will lead to more accurate prediction in the future. So that is why there are different ways by which we can assimilate the radar data to improve the short range prediction in different ways. So these two are going to be the new era of data assimilation especially when it comes to polarimetric radar data assimilation. So there are quality controlling is very much important, but there are different error sources associated with the radar data. First group is hardware error. Then this is already covered by the previous speakers. The second group is related to the radar beam geometry, and then third group is related to the echoes from non-precipitating or the non-meteorological targets, and then the fourth group is related to the beam blocking attenuation signal, even from the atmospheric processes and all. So these are some of these also we need to address, because quality control is one of the main thing, because the quality of the data is very much important to when it is coming to assimilation. So that depends on the entire process of data assimilation, further forecasting actually depends on this quality control. So that is very much important. And then when it comes to application of radar data, there are many applications, but process understanding is the main thing. With the radar data, we will get a fine scale structure of the convective storms. That is the main beauty of the radar. So that has to be translated to the model. If you look at any model, global models or regional models, which is using parameterization scheme, all these models are lacking mainly because of the accurate representation of the condensational heating So this is a because that is what the radar data with the dual polarization capability that will guide the model in formulating the accurate formulating the parameterization schemes. So that is what the radar data, rather than validating or validating the model observation with the radar data itself can guide us to modify the parameterization schemes. That is one of the, because that is very much important. So this is one example from the ARM cloud radar simulator, where on the left side it is the um, real radar data. On the right side, it is a ARM simulated data. So this is why this simulation is also guided by the radar data, so that still the simulated profile is not matching with the actual observed profile of the radar data. So this is actually a problem. This is actually a problem in most of the models. This is a very theoretical model studies, but still that type of model itself is not able to capture the actual vertical profile of the convective storms. So that is why when it comes to process understanding, most of this understanding from the radar derived products should go in improving the parameterization schemes in the model. And this is another issue is with the merging of data, because if you look at this is a dense network of observation from Meteor France mosaic, where there are radar data and also rain gauge data. They are almost like 26 rain gauge data deployed over this small catchment area, where they have a radar as well, and they compared the rain gauge estimated rain rate and the radar estimated rain rate. They found that most of these times the radar estimated rain rate is underestimating. So that is the biggest problem when it is coming to a very heavy rain classes. So this is may not be the problem always, but it seems that it has a larger underestimation and the bias associated with estimating the rainfall during the high rainfall cases. So and if you look at the time series of this based on the dash curve is from the rain gauge, and the solid curve is the radar estimation, and the red shaded is the uncertainty in the radar estimation. We can see that the radar estimated rainfall is most of the time it is underestimating. If you look at the cumulative curve also, this is the dash line is the rain gauge accumulation, but it is always the radar derived or the radar estimated rainfall is always underestimated when it is coming to the high rainfall cases. So this is how some of the merging problem or the compare, and if you look at it, we don't have a kind of when we want to composite radar data from different uh, types of radar. So that is also a very complex issue, because if you look at the Meteor France dense network of radar, they have C-band, X-band, and S-band radar. Some of this C-band and X-band radars are coinciding over some area. So that means with this C-band and X-band radar, they observed the same rain category over a particular region, and then they estimated the rain estimation from both C-band and X-band. What they found is that C-band is overestimating and X-band is we cannot say that it is overestimating. They are not. It is higher compared to the X-band rain estimation. So in this case, C-band is overestimating compared to the actual rain observation. And if you look at the spatial distribution of this rain, the C-band, which is resolution is slightly coarse compared to the X-band. So the rainfall, the spatial distribution of the rainfall is also very much different between C-band and X-band, because one thing is that the C-band, they are more polarimetric radar. They use the rain estimation based on the ZR relationship. So that is the one thing. Though we all are using this Marshall-Palmer ZR relationship with the different variants, but still this is widely being used, because maybe if you look at the radar data and rain estimation, probably Marshall-Palmer, this paper may be cited maybe the highest in the radar estimated rainfall case. So And when it comes to X-band radar with a dual polarimetry, so there the rain estimation is based on the KDP, where there are some certain classification or the threshold limit if the KDP is used below 35 dBc, the rain is estimated with ZDR relationship. Then high reflectivity case only KDP with high KDP value, then only they use rain estimation from KDP. So this is what different radar system will observe or estimate different rainfall rate for a particular event. So that is what the challenge. So when merging, that is what the challenges in the merging. When we merge all this data together, so it's a very, very difficult job because, and another thing is that most of this radar may not be tuned. The ZR relationship may not be tuned with the distrometer data, and also there are no much dense network of rain gauges are not available, and also range problems when it is coming to higher ranges, because both the radar may be located at different locations, but they are observing at a particular point, means the range associated with the C band may be different and the range associated with the X band may be different. So all these issues are very prominent when we talk about radar. So when we talk about the radar data and the radar data merging, compositing using radar data, it is in the primitive stage, because even in India also we have dense network of radar is coming up. A lot of opportunity to merge all this type of radar data to make the mosaic, and then the merging issues more prominent when it comes to coincide two type of radar. So that is what another issue regarding that is another, because what I want to present before the audience is the lot of opportunities exist in the radar data assimilation and deriving useful products from the different multiple radars. So that is what the lot of skilled manpower is required in that direction. And also it depends. If you look at the another application, hydrological, high resolution hydrological means catchment level or the urban scale hydrological studies, we required like X-band type of radar with a high resolution rainfall estimation. This is another because all this radar, X-band radar and C-band radar data what we are estimated over that catchment area, that is going to the input for the hydrological model. There are different type of hydrological model. In this case, they have used two type of hydrological model. One is the distributed, the physical model, and another is the very primitive type of semi-distributed model, where rainfall runoff is the main thing they are considering. And another and if the same model, but because if the same model which is forced with the C-band estimator radar and X-band estimator radar, they will give, ultimately they will give different runoff values and the water depth values and all. So that is what the estimation of the radar when it comes to hydrological application, the accuracy of the rainfall estimation is also very much important. It is not just, what I want to say here is that it is not just about the rainfall accuracy. There are a lot of uncertainty also emerges from the hydrological model itself. Because if you look at the hydrological models, they are mostly tuned for particular catchment or a particular urban area or the hydrological domain or the watershed area. That is most of the parameters which is used in the hydrological model, they are calibrated for a particular type of landscape or the domain or watershed or the hydrological domain. So that may not be accurate when the same model is being used. Like for example, most widely used hydrological model is the ACARR. That is a hydrodynamic model. That itself, a lot of tuning is also required when it comes to hydrological models. So that means the error, when it is the final error of estimation of depth of the flood or the hydrological runoff is not only contributed from the estimation of the rainfall error, the uncertainty estimation uncertainty associated with the rainfall error, but also it is contributed from the hydrological model uncertainties itself. What I want to say is that these both will cascade together and will give a lot of uncertainty when it comes to final products. So that is what these are some of the other challenges as far as hydrological modeling with when we force with high resolution radar rainfall estimate. That is also needs to be as another opportunity in the future, because most of the urban areas and the watershed, the river basin, most of the river basin are going to be equipped with the kind of hydrological models where this type of radar derived rainfall product is going to be one of the crucial parameters for forcing these hydrological models. And also, there are different ways by which we can estimate the optimum time resolution based on the catchment area. This is another for urban scale hydrology. We need time resolution of the order of 2 to 3 minutes, and for a particular catchment area of up to 5 square kilometers. So this is another way of estimating how what temporal resolution is required for estimating the hydrological input. And another problem or another opportunity arises from the merging of different type of data, especially for the nowcast applications. Because we have different source of data coming up regularly, because like the frequency, that is what the big data is coming up every second. Data is coming up from the satellite, from the model, and from the radar. So final nowcasting product should be a combination of all these things. They were kind of adaptive blending algorithm. Nowadays, machine learning is coming up as a useful tool, but still there are a lot of problems there. But otherwise, how we can optimally merge all these products together to come up with our final nowcasting output. So that the merging of all this, or blending of all this product, including satellite models and high resolution models and the radar data, that is also going to be another hot topic, or a lot of effort required in that direction as well. Because considering all these things, a lot of challenges and lot of opportunities exist before us. So what we need to do is that we have to come up with a lot of manpower, skilled manpower, to tackle all these issues. What I want to express here is that there are a lot of problems. We have to come up with solutions. So when it comes to dual polarimetric radars, a single, this is a supercell storm with a hook echo type of pattern, which is shown as in the reflectivity. Correspondingly, there are dual polarimetric parameters like KDP is ZDR is there, 5D means differential phase is there, correlation coefficient is there. So that means with a different type of parameters, we will get a different information regarding this scene. So that means lots of opportunities are there in the polarimetric radar data, and its utilization. It is very still limited, because another thing regarding polarimetric radar is that it is a relative measure. Whatever we are measuring as KDP or ZDR, they are not absolute measures of the true value. So that is another problem. That is why this polarimetric radars are not widely utilized, and it is underutilized. We can say that the polarimetric radar data is utilized for understanding the physical process, understanding the cloud structure, understanding the classifying the clouds. These are there, but otherwise, when it comes to direct utilization of this PRD products, it's very underutilized due to many factors, like it is a relative measure compared to the horizontal or vertical polarization. So that it also depends on the environment as well, because it has different values when it is raining, drizzling, snowing. All this, the parameters associated with this can also vary. So that is why this is the main challenge which is facing in the case of polarimetric radar data application and the utilization. This relative measure is the main limiting factor. There is no absolute measure of that particular parameter. That is where we have to make some kind of observation operator to map all this polarimetric data polarimetric related products to the NWP counterpart. So that is another one. And also classification cannot be always accurate because of the radar volume itself is containing different type of processors. Already, I think this part is already, the classification part is already covered by the T.N. Rao sir. And then another main issue is most of the polarimetric radar are also, they are also trying to utilize the power law type of polarimetric. When it comes to mapping the polarimetric information to the radar, other radar products or the NWP related state variables, it is also, the rain estimation is still depending on that power law. So that is what another limiting factor. That also we convert into linear scale by. That is the main beauty of this Palmer Marshall equation. But that is when logarithm we are taking it is on the linear scale. So that is on another limiting factor, where drop size distribution in a linear fashion, how to estimate that how to map that to the model variables. That is another thing. So that means difficulty involved in using that also still continues. Large variety of uncertainty in storm scale model itself contain large uncertainty. The high resolution model itself contain large uncertainty. That also we need to address. So that means the model parameterization is still lacking to represent. That is what the mapping of variables between the polarimetric radar and the high resolution mesoscale model. That is also very limited, because not only because of the polarimetric deficiencies or the uncertainty in the polarimetric observation, but also the uncertainty in the NWP model itself also contributing to this. The disconnect between that is what the disconnect between the model basic state variables to the polarimetric variables. And what is a way forward? The effort has to be made to develop PRD simulation, like the forward operator, to connect the model variables, including the polarimetric variables, to map the observation to the model variables. So one way to advance this is to improve the model parameterization itself. That is what one way the polarimetric radar, which has to be utilized to improve the parameterization. That improved parameterization or the improved model will aid in taking the polarimetric observations back to the model. So this way, this is a kind of two-way, because one way it is improving the model parameterization. That improved model can be used to make more accurate observation operator pertaining to the polarimetric radar data assimilations. And then the error observation information, they are not enough, or the observation. That means when we mapping the drop size distribution, it is not distributed. Like drop size distribution normally coming from the distrometer, that is also not uniformly distributed. The observation itself is not uniformly observation itself, in the sense that the validation observation or the mapping observation, that is also not continuously distributed across the domain. That is one of the another drawback. So that's why we need to invest more on this mapping, this type of polarimetric observation to these model state variables, like drop size distribution, axis ratio, density, orientation angles. All these parameters has to be mapped, and then we need to create forward models for observation operators to map this variable back to this observation or the model state variable. Here, it is almost like equivalent to a variational data assimilation problem, or the variational problem, where we are actually minimizing the error associated with this. But that error, the observation counterpart is not available everywhere. That is what the limiting factor. Then we can use ensemble Kalman filtering based analysis as a forward operator. There we can assume the forward operator to be the linear, and the flow dependent covariance background metrics can be estimated from a limited number of ensemble observations. So that ensemble Kalman filter can be utilized here to estimate accurate estimation of the model state parameters through observation operator. And then we can also utilize, because there are when we the way forward is like when we utilize the polarimetric radar data, there are two parts: the DA based data assimilation based derived products, and also the observation based derived products. The observation based products can be derived through the in situ measurements, processing, analysis, and then the observation, classification, estimation, and the QC check and Garrett's observation based retrieval can be used, and then that can be merged with the model based data assimilation techniques, like the model based the parameterization improvement and the parameterization better parameterization selection, which is guided by polarimetric observation to improve the model NWP model and the selection of the model and the advancement of the model, and then better background error estimation, like from the PDR techniques, and then that leads to the data assimilation retrieval. That also this assimilated these process also in turn help the observation based retrieval in actually when it comes to further making assimilation modeling or the microphysical modeling. So this way, finally, what is the output is that all this process has to be in tune with to estimate better QPE or the other products. So that's what the future of this radar data assimilation is, kind of estimating useful parameters from polarimetric radar data, and where the machine learning based radar data means precipitation estimation is also as a coming up as a emerging technology, and also multi-source precipitation estimation and blending, another area where AML can contribute much to make the merging of different type of observation together. There are not only the radar for the nowcasting purposes, radar data, satellite data, NWP model, all has to be merged together in an optimal way, so where AML can contribute much, and then we can create conceptual model where this all physical things, especially when it comes to the forward observation operator, we can come up with a better forward model which captures the more variability very accurately and reliably. So in a nutshell, what are the opportunities related to radar data analysis or the application on research? There are plenty of opportunities and plenty of challenges. We have to make all these challenges as opportunities to come up with a better prediction of the atmospheric parameters, like we have a lot to contribute towards process understanding that intent improve the parameterization. We have to lot to contribute to the initial analysis, like data assimilation, different type of data assimilation, forward operators and all. So to come up with the best estimate, that also we can, there are a lot of effort is required. And the nowcasting, especially post-processing, where the merging of the data. And finally, the technology is also coming up, like multi-functionalities, because now the phased array radar is also being converted to make the Doppler capability, to make Doppler weather radar capability. That multi functionality and also multiple range resolution, multiple frequency options, adaptive beam forming techniques. All this can contribute to the in the technological side, and then the QP estimation and the merging product. So these are some of the areas where the maybe another next 5 to 10 years will see lot of improvements. This way only we can improve our numerical weather prediction and the better understanding of our process, and also to make our nowcasting and short range weather forecasting more accurate through all this combined process. So this is where a lot of opportunities are there in terms of radar data analysis and in terms of research, and also, and finally, both will contribute to the operational prediction of weather parameters in the future. So I will stop here. Thank you. Thank you.
Thank you, Abhilash, sir, for this lecture. Now it's a Q&A session. Lakshmi Kumar sir is not there. I invite Dr. Rohini madam to conduct the Q&A session.
Yeah, I don't see any questions at present. So I request the participants to please type your questions in the Q&A box. Meanwhile, can I ask one question?
Yes, yes.
The Marshall-Palmer equation, which says A value as 200 and B value as 1.6, is it the same fixed value used even for the Indian region? Because these A and B constants change according to location, what we have found.
Yeah, it is not same for all locations. We have to tune those A and B for a particular location, particular season, type of rainfall, type of clouds. Everything needs to be tuned based on the distrometer observations. That is also surface, but micro rain radar data is there in the vertical up to 5 kilometers. So all this data together can be used to um, estimate the best parameters for a particular location, and also that may not be correct for a single radar, because the radar covering area will be different. So even for a single radar itself, we maybe have to have a different type of A and B for different regions and different ranges. So all this is very much critical. Yeah.
So even for the rain type, it will change, right?
Yes,
Stratiform
yes,
and convective, yeah.
yes.
One more question. So
Also
you
frequency
showed
also.
the variability, right? After data assimilation, the rainfall variability. So there were still some discrepancies. The after assimilation, there were though it was better than the previous whatever model showed, but still, what do you think? Why the discrepancies may be there even after data? Because eventually we think that if we assimilate the data, maybe it will improve it. It improved, but not really much. So what can be the reason?
There can be two reasons for this, because we have used the 3D war scheme, because that is not a like a rapid assimilation scheme where we consider plus or minus 3 hour window, the batch of observation coming in that window as together for that particular time. So that is also that time is very much important. So that is why either 4D or ensemble Kalman filter, where the background error is updated, adaptive background error is also very much important. So that is also like a 4D war, and if ensemble Kalman filter type of assimilation scheme, if you implement, it can further improve. So that is two things, right? One is that observation operator also contributes to the error, so that also we have to fine tune. Another is the frequency of means how instantaneously, like 4D war, which consider each observation at that instant, particular instant, that also affects this. So that means we need a more high resolution observational means data, and also more frequent assimilation in a rapid assimilation cycle. So all this contribute to that.
Okay, thank you. Yeah. So I still don't see any questions. I think they are all clear, very clear about
I
what
don't know,
you
may
said.
be clear or maybe not clear.
No, it was very nice talk, and it was very, I mean, you explained it very nicely. So are there any questions on the YouTube? Can someone
No,
check?
no, madam. We are checked. There is no
Okay.
question to the YouTube.
Then over to you, Dr.
Okay.
Rakesh.
Thank you, madam. Sir, Ramesh sir, can I give some words, concluding words? Sir, you are mute, sir.
What about the photo session?
Sir, I will conduct. Okay, we'll take.
Done. Mr. Sahalam is still, I think, not visible. Now he is visible.
Yes.
Okay. Okay.
Okay, ready? Okay, take. Done, sir, done.
Okay. Well, thank you very much, Dr. Abhilash. for summarizing the challenges and opportunities in the application of radar data for research. You have rightly discussed in the beginning about how we can assimilate the data in the model for improving the forecasts. That's very correct. Also, of course, I can see that the attendance has thinned down to for 36, 37, probably because although it is supposed to be one of the very important topic, because as I said in the beginning, that most of the participants may be interested in the application of radar data for research rather than the technical or engineering aspects of radar. But in spite of that, I see the attendance is thin at the end, although initially it was about 78 or so, or roughly 80, but now it is thin. One reason could be, I do not know, maybe because there were certain things probably which many of the participants might not have even heard about it, like the application of Kalman filter, etc. in the data simulation, 3D VAR and 4D VAR. Maybe it may be something totally new to the audience, because unless they study the data simulation, they may not know what exactly is the 3D VAR and 4D VAR. So for that reason, it could be the attendance may be less. But the thing is, it is a very important topic, and Doppler radar is the most important tool if you want to do research on the convective scale data simulation, especially the so-called rapid update cycle, because Doppler radar can provide you the aerial distribution of the three-dimensional structure of the atmosphere, which is so important. And as you know, we have the scan strategy about 10 minutes. So Doppler radar can provide you data for at every 10 minutes and for the entire aerial region of the domain, which other conventional data which are taken normally at the synoptic hours, like hourly or 3-hourly or 6-hourly, those things cannot be used for rapid scale if you want to do it at every 1 hour time interval simulation. So that is one of the important applications of Doppler radar. Also, if you want to construct the three-dimensional structure of the convective storm, for example, what is the vertical distribution of the cloud microphysical parameters, or what is the vertical distribution of the velocity field, wind field inside a typical thunderstorm, then Doppler radar, especially the polarimetric Doppler radars, are very, very important, which other instruments like space-based satellite etc. may not be able to provide you so much data for that particular research. I think another thing probably Dr. Abhilash did not get the time. Maybe he could have also spoken about the MST radar, the application of MST radar in the research in meteorology, because he is the director of the center which has basically the MST radar in India, and it is so important, especially if we want to measure the convective vertical velocity. Then ordinary instruments do not provide us the convective vertical velocity which the MST radar provides throughout the troposphere. So that application probably there was not sufficient time to cover that, because that is again totally a new chapter, a new area. It requires a lot of elaboration. But overall, thank you very much, Dr. Abhilash, for covering the challenges and opportunities. As you said, now there are a lot of opportunities of research. Many things are still unexplored. And as you know, in India itself, there are so many radars already existing, and we have plans to cover the entire country by an umbrella of more than 80, 85 Doppler radars. Already about 40 radars are existing. Also, in other countries like Bangladesh has got 4 or 5 Doppler radars. Nepal has got 3 Doppler radars. Pakistan also has many Doppler radars. So like that, every country, every meteorological services have now by and large got the Doppler radars, and therefore a lot of opportunities are there for research. Not many things are still explored, they are unexplored. So this lecture was one of the very, very important topic in that research. I think also the next lecture, which Dr. Mohan Kumar is supposed to take, he will also be talking about the application of radar for research. So you will hear more about that in the next lecture by Dr. Mohan. And by this, with this, we have almost come to the end of this lecture series. After Dr. Abhilash talk, there will be talk by Dr. Mohan Kumar, and afterwards we have got a talk by industrialists or I mean people who manufacture the radars. They will tell us about the difficulties or challenges in designing different radars for research purposes as well as for the operational purposes. And that will be the end of it. And after that, there will be a test. I hope that all the participants are attending regularly the lectures and they will be prepared well. We will announce the exact date for the final test. Hopefully, it will be as per the time schedule, but sometimes it might be delayed by 1 week or so, depending upon many factors. But it will be held hopefully in November itself, and then at the end we will have a valedictory function. So we have almost covered the entire lecture series on radar meteorology, except for few more lectures which are left, and it will be covered by next month. And I would just like to announce now itself that after this lecture series on radar meteorology, SAMA is now planning to have another lecture series on atmospheric dynamics and its application to weather and climate modeling. And thanks to Dr. Rohini, Pune University has kindly agreed to be the host for this lecture series on atmospheric dynamics. That is also a very important subject. And it's likely that it will go on for about 6 months, more than 24 lectures probably we're planning for that. So it's going to be another important topic, which will start by, I think by January, third week of January, we are planning to start that. So hopefully we'll announce that all in due course with all this brochure and then registration link for that. But anyway, thank you all for being present till now. Today we are a little bit late because of the technical issues in the beginning. But thank you so much once again. Yes, over to you, Dr.
Thank you, sir. I invite Aditya sir to give some remarks.
Sir, are you there? Please mute. Your mutes.
He is not responding.
Oh no, he's
Hello.
Nice.
Yeah.
Am I audible?
Yeah. Yes,
sir.
yes.
Okay. So no doubt we had a series of lectures, and over a period of time the numbers have come down. There are two reasons are there, that when there is one quantity and one quality part. So when high-end presentations are there, what we really appreciate that even now 50 odd plus I think participants are motivated and committed to attend such lectures and benefit from it. So 50 researchers, we are able to motivate them to take up this, it's a big achievement. So we do have, since we have a wide spectrum of participants, to expect that all of them will attend all lectures, or at least the high-end lectures is not there. So I really commend all those participants who are continuing to participate, and my request to them will be there, benefit from here. And I'm sure if you contact Dr. Abhilash for further guidance and what research, if you want to apply for research in radar meteorology or radar applications, I think he will be able to guide you. So I think the number which attended today is a potential researchers in the future, and we wish them all the best. Thank you.
Thank you, sir. Now it's time for vote of thanks. I invite Dr. Mohan Kumar Das sir for presenting the vote of thanks.
Thank you. Distinguished speakers, esteemed guests, and valuable participants. It is with great honor and profound appreciation that I extend our deepest thanks on behalf of the SAMA and ACARR and organizing committee to Dr. S. Abhilash, Director of ACARR, CUSAT. We are truly grateful for your illuminating presentation on Doppler radar applications for research. Your insights have not only broadened our understanding, but have also sparked inspiration among us all. A sincere thank you to Professor Dr. Someshwar Das sir for your thoughtful welcome, and to Air Vice Marshal retired Professor Dr. Udit Tyagi sir for your words of wisdom, steering the course of today's session with elegance. We're also indebted to Dr. Rohini Bhawat for a warm and engaging introduction of our distinguished speaker. Professor Dr. Lakshmi Kumar, your skillful navigation of the question answer session and enabled a stimulating exchange of ideas. Thank you for your ensuring that curiosity met clarity. And thank you, Dr. Rohini, to conduct the session also. Our appreciation also extends to Mr. Rakesh V, whose continuation moderation kept the session flowing effortlessly. Lastly, to every participant, your presence and thoughtful engagement are the heart of this gathering. We are truly humbled by the global community's enthusiasm, which has elevated this event to its pinnacle of success. With warm gratitude, we look forward to continue this enriching journey with all of you. Thank you once again, and may today's knowledge propel you forward. Thank you.
Thank you, sir, for the vote of thanks. So now we will conclude the section.
I think you can shut down. YouTube will close automatically, right?
So you have to stop it, stop live thing.
Is it? Will it not
Yes.
stop automatically?
It will be keep on going. It will
First
not
of all,
stop.
you stop recording. You got to stop recording and
Stop it at live stream.
I think if we leave, end the meeting, it will stop on YouTube also. That is what
yeah, I think
the
so. I think so.
Automatically.
Yeah.
I think so. So please stop.
Post in here.
But I don't see the stop button for YouTube.
അതെ നോക്കണം.
host can have it.